right, let's do that assembly example where we're going to write some assembly code from scratch. Specifically, we saw earlier some code that added 1 to a number. Let's write a program that's going to add 2 to a number. So I'm going to create a file called add2.s, and we're going to write assembly code just from scratch. So first thing we're going to do is we're going to specify that the main function is publicly available. This is like saying public in Java. You don't have to do this in C, you do have to do this in assembly. Then we're going to write our add2 function. So add2 is a function. Functions start with enter 0, 0 and end with leave ret. That's not exactly what the compiler did, but that's the pattern that we're going to be following in this class. Every function starts with enter. We'll talk about what these are later, and it ends with leave ret. In here, what we're going to do is we're going to take the first argument. So in assembly, we have, according to the AMD64 instruction set architecture, standards for writing programs on Linux, the way we pass arguments to a function is in registers. So the first argument register is RDI. Second one is RSI, so if we have 2 arguments, the second one goes in RSI, but add2 is a pretty simple function. In fact, add2 takes x and it's going to return x plus 2. That's the whole function. So x here is RDI, and we can go ahead and say that we're going to add 2 to RDI. So now we have x plus 2, but then we have to return it. To return it, we need a return register. Again, the AMD64 on Linux convention says that we return a value, an integer-looking value from a function in the RAX register. So we could do move RDI into RAX, and then we have this is like x equals x plus 1, or sorry, plus 2, and then this is like return x. So there is our add2 function written in AMD64 assembly. We need one more function in this program. Again, enter 0, 0, leave ret. Now, what our program did before is it called printf. There's some tricky pieces that we need. So we're going to need to define that string. Now, one complication with assembly programs is that the assembly source code is saying what's going to go into the executable program file. The executable program file has multiple sections. Code goes in a section called text, and then data goes in a section called data. So in our data section, we're going to go ahead and say that we have a string called long format, which is a string, and it's just going to contain %ld. That's the string that we want to pass to printf. So then to call printf, we say mov long format into RDI, that's the first argument register. We're going to mov 5 into RDI. So we're going to say x equals 5 here, long x equals 5. We're going to call add2. So this is going to call our add2 function. First argument register is RDI. 5 is already there. Result is going to come back in RAX. That's the return register. So then we want to pass our second argument to printf. This is printf like that. Oh my god, it's moving my typing. Emacs is annoying in assembler mode. There actually isn't really a great editor for doing what I want to do when I'm typing assembler. Vim is a little bit better than Emacs, but Emacs is okay. In any case, I'm going to mov that value rax, which is where the return value from add2 was, into that second argument register, which was rsi. And then we want to call printf. Now there's one more awkward thing about the calling conventions for AMD64 assembly, how we call functions. The calling conventions specify argument registers, they specify return registers. One more thing that they specify is how to call variable argument functions. Printf is funny. Most functions in C take a constant number of arguments, but printf can take any number of arguments. The first argument is this format string, and then any arguments after that are telling us what values to sort of inject into the string that we're building. So if we had ld, we could add y, and then this would be the first integer, that would be the second integer, etc. We're not doing that. In any case, when we're calling a function like printf that takes multiple arguments, let me go ahead and look at the man page for printf. So here's the official documentation for printf. We can look at documentation for all kinds of things under Linux, both C standard library stuff, system calls, standard programs. We can look at them by looking at the manual page. But here's the manual page for printf saying what the signature of the function is, and the function signature has this ... in it, which means it's a variable argument function. So whenever we have a variable argument function, what we need to do is we need to specify, before we call the function, we need to specify how many vector registers we want to pass as arguments. And I'm not even going to explain what a vector register is, because we're not going to be using vector registers for at least most of the semester. So it's always going to end up being 0. I shouldn't say always. It's almost always going to end up being 0. Definitely for the first couple weeks of class, it's going to be 0 vector registers. But we still need to specify it because it's part of the calling convention. So we're going to move 0 to AL. And if you'll remember from register naming, this is the lower 8 bits of AX. So it wasn't actually 0 before, it was 7, which is wrong. That would cause our program to crash because we would be passing the wrong information to printf. Now we want to move a 0 to rax because we're going to return 0 from the main function. Returning 0 from the main function indicates a successful termination of the program. And there is our complete assembly thing. Now to compile this, we need to say gcc add2. We need to add2.s run. And if we just try to do that, we get this error message that says we can't compile our data section because we're trying to make a pie and we need to recompile with fpic. If we try to recompile with fpic, that won't work. This is because we're writing our program in a way that isn't compatible with position-independent code, which is a security feature that's available in modern Linux systems. You'll remember that when the compiler generated a call to printf, it said printf at something. We're not doing that. You need that for position-independent code. So instead, we're going to just go ahead and say no pi. We do not want a position-independent executable. We don't care about that particular security mitigation right now. We're just trying to figure out how assembly works. So if we ask for no pi, it will compile. and we have a program that successfully prints 7. So that is how we can write a simple assembly program. All right, next topic that I want to talk about is homework 1. Homework 1, to find, we're going to go look in this web browser, and we're going to go to inkfish.ntuck-neu.site. And I assume that nobody's actually registered for both of these courses, but you'll click, well, first what you need to do is click list all courses, and then you have to request access to 3650, and I have to approve you, and that's going to take at least 24 hours, so you want to do that as soon as possible. But once you've done that, you can click CS3650, click homework 1, and here is the description of homework 1. You have to do 2 things. The first thing that you need to do is install a Linux virtual machine with VirtualBox. So 64-bit Debian 10 on VirtualBox. There's a guide here that might help a little bit, but setting up that particular VM with that particular technology is required for this first homework. Once you've done that, you have to install the screen fetch program, which just prints a thing, screen fetch. It says you're running Debian. I want to see that you're running Debian. You want to take a screenshot of that. The screenshot should take the full, should cover the full VirtualBox VM window. We can see that you're really running in VirtualBox. And then, yeah, that's the first task that you need to do. Some notes here that are important to read. Sharing directories with the host operating system, not using a VM. These are things that you can do, but they potentially cause problems, so you want to be careful with them. Using the VM is not actually required for anything but this one screenshot, but I want to make sure that you're able to install it because that makes sure that everybody is able to do the homework. If you come up with some way to like try to do this on Mac, which will work for the first couple of weeks and then not work, try to do this on Windows using WSL, which will work for the first couple of weeks and then not work. If you want to get that sort of thing to work, go ahead and do it. If you come complaining to office hours saying it doesn't work, we're going to ask you, have you tried it in the VM? Then you're going to try it in the VM, and maybe it'll just work. In any case, the second task that you need to do here is to get an account on, or you should have a Linux account on with Curry, because it's required in order to log into Inkfish. So if you're here, you've already done this step, but in order to log into Inkfish, you may have to go to my.ccs.neu.edu and sign up for an account. And then you need to SSH into the shared Curry Linux server. It's called login.ccs.neu.edu, and you can connect with an SSH client. On Linux, that's just the SSH command. Once you've done that, you want to do these steps, which will result in an output file that the TAs will be able to check to make sure that you did successfully log into this server. So that gives you a screenshot and a text file. The other part of this homework is that you need to write some code. And this isn't really about writing code. The code that you're writing is a function that squares a number and a function that cubes a number in C and assembly, which is relatively trivial. I've shown you all the pieces that you need to be able to do those things. The important thing is the mechanism of doing homework using Inkfish. So in order to do an assignment on Inkfish, you're going to start with starter code, which comes in this tar archive. You're going to have to be able to download this tar archive. You're going to have to be able to extract that tar archive. You're going to have to be able to go into this directory that you got, edit the starter code or add files to the starter code. You're going to have to be able to successfully build it. And then you're going to want to be able to run the test script. Now the test script that I give you in the starter code is the same test script that's going to run on the Inkfish server. And with the starter code here, all the tests failed. So if I submitted this, I wouldn't get any points. But once you're done doing this, let me actually go ahead and see if I can do part of this. So it's saying that we need to create a file called square.c, I think. So we'll create a file called square.c. So we'll do that. That square.c file is now going to have a thing in it. Now if we do perl test.pl, we pass some tests. I'll probably lose some points when the TAs grade this because my formatting was terrible. That's something that they do check. Having your entire program all in one line is bad style. The style rules that you have to have some consistent, reasonable style, and that's not a reasonable style, so I wouldn't get points for it. But I'm going to clean up the stuff so I don't have any binaries or anything, because it says that I shouldn't submit any binaries. It's going to say I shouldn't have any extra binaries once I edit it in a second, but you want to run make clean before submitting anything, and then you tar it back up. tar czvf starter. I guess I can just say ntuck homework1.tar.gz, that's the name of the file, tar up that starter directory, and now I have my homework submission thing. I say new submission, I say browse, I want scratch 01 my homework. So it's uploaded, I press submit. Oh, I should fill in how many hours that took me. I'll be like most of the students in this class last semester and be like 370 hours because that was a really hard assignment. And then immediately when I upload it, it's going to go ahead and run the test script. And it turns out that it passed 3 tests. And so the score I got was 20 out of 50. You can see, well, if I reload the page, you can see that my score is 20 out of 50 on the script portion of the score. We don't have a total score yet because there's also an element where the TAs are supposed to manually grade it. But these points, as long as I was honest in doing the assignment, and I really did solve that piece of the assignment, those points are points that I actually have. They're not gonna, I'm not gonna like lose those points because the TA decided that the rubric had changed. I really wrote the function in C as per the instructions, and it passed the tests, and so I'll get the points. So that's homework 1, and that's due on Monday. Yeah, I think that's the whole story, and I better delete this partial solution for the homework from this scratch directory before I share it on Git. Good luck with the homework. See you in, well, you've probably already come to lecture 1 realistically, but see you in the next in-person meeting or in Zoom or in the next lecture or something. How do I stop this recording?